All right, this is Mr. Gillum, and today we're going to talk about some similarity transformations. So we've talked about transformations in the past, but only really gone into detail with rigid motions, translations, reflections, rotations, glide reflections, those types of things. But today we're going to actually start talking about dilations, which is the stretch or the compress of an object. And so we also call it, instead of stretch and compress, we might call it an enlarge or a condense. And so I know it looks like there's a lot of information here, but a lot of this stuff is stuff you've heard before. Okay, a dilation just basically stretches or compresses the pre-image, the identity. So I guess the important parts would be an enlarge or a reduction. Okay, it's a type of transformation, but it's not a rigid motion. And there's a point that doesn't change, it never moves. It's called the point of, or the center of dilation. All right. The scale factor dilation describes the extent of the dilation. Okay, so the scale factor, we're going back to scale factors again. Now, we talked about scale factors before. It's the same kind of deal. Okay, but this is the important. It's the ratio of the length of an image to the corresponding length of the pre-image. So it's always from image on the top, pre-image on the bottom. That's really important. Okay, image over pre-image. Okay, the lengths of corresponding sides. All right. We're going to use the scale factor as k. Okay, it's going to be our scale factor variable, kind of like m is always slope. K is going to be our scale factor in this case. And if the number is bigger than 1, it's going to be an enlargement, or if it's less than 1, it's going to be a reduction. So if you look at the diagram here, it says triangle JKL is a dilation of triangle ABC with the center of dilation at 0, 0. Okay, and the scale factor is JK to AB. So in this case, we would compare JK on the top, that distance, to AB on the bottom, that distance. And that scale factor obviously would be, if we're talking about image to pre-image, this would also obviously be an enlargement or a stretch, because the identity is getting bigger. So it's a stretch. So the scale factor should be bigger than 1. Which is what I want to talk about right now. Okay, for enlargement, the dilation with a scale factor greater than 1 produces an enlargement. And that just means the image is bigger than the original. So always compare the image over pre-image. Okay, that's important because that's going to tell you, if you do it the other way around, you're going to get mixed up on enlargement compared to reduction. Okay, so if this must have been the pre-image, and this is the image right here. And as you can see, it got bigger, so we call it enlargement. So it's pretty straightforward. Reduction obviously is what is getting smaller, compressed, reduced. So this one in this case would be the pre-image, and this would be the image itself. As you can see, oh, I'm sorry, I said that wrong. This guy, A, B, C, D, would be the pre-image, and now this is the image itself. So it's gotten smaller. So when I say it's less than 1, I mean in between 0 and 1. We would never have any scale factors that are 0 or less than 0, obviously. So when I say less than 1, I'm generalizing, making under the understanding that it's impossible to have 0 or less than 0 as a scale factor, as far as a negative would be concerned. So from a big pre-image to a small image would be a reduction, and the scale factor should be in between 0 and 1. All right. So let's take a look at this dilation and just kind of decide just by eyeballing it what is actually happening. I'm going from A to B, so obviously A is the bigger triangle and B is the smaller triangle, and so this is going to be obviously a reduction or a compression. Okay, so when we're comparing these two things, we always need to think, okay, what is my scale factor? And so to do that, I need to compare my image to my pre-image. All right, and so I just need a corresponding side of each. Now, I could pick any of these sides as corresponding sides, those two, or these two right here. But really, these are going to be the easiest because I don't have to use the distance formula to find how long they are. I'm going to use this distance right here for my pre-image and this distance right here for my image itself. So my image distance goes from negative 1.5 to positive 1.5. So 1, 2, 3, a distance of 3. And my pre-image, where I started, has a distance of 1, 2, 3, 4, 5, 6. Okay, so in this case, my scale factor, or represented by K, would equal 1/2, and that does represent a compression. which makes sense because we can obviously see that image A, sorry, the pre-image and the image itself, the image has gotten smaller from A. So you can see kind of how it works. It's pretty straightforward. Now your examples, you might need to, if it's tilted on the axis, you might not be able to just count and see how long each side is. You have to use the distance formula. But for now, it's okay. There's a little sentence down there too that says you can always verify that a dilation produces a similar figure by comparing corresponding sides and angles. Or you can use side angle side for triangles, but not all polygons are triangles. So like this one, for instance. Once again, I'm going to tell you, be strategic when you're looking at your dilations. We're going from A to B again, and obviously A is the smaller one, and it's getting bigger. So right away, I'm thinking that we have an enlargement or a stretch. Okay, and so let's find the scale factor. And the scale factor is a comparison of the image to the pre-image. And so I want you to be smart about where you pick. Now I could pick this guy and this guy, but I'm going to have to use a distance formula. Or I could pick these two to compare, and that's not going to be good either. I see that these will be very easy to see the distance of these lines right here, these segments, these sides of this polygon. So those are the ones I'm going to choose to look at. So for my image, my final part, 1, 2, 3, 4, that side has a distance of 4. And for my pre-image, 1, 2, 3, a pre-image of 3. So in this case, as you can see, my scale factor is 1 1/3 or 4/3. Either way you're at it, it's bigger than 1. So therefore, my scale factor has shown that I have an enlargement or a stretch this time. Okay? So let's take a look here. And what we're going to do is we're going to verify that these two triangles are similar. Okay, it doesn't promise us they're similar. We need to know that they're similar though. So our specific instructions say graph the original figure in its dilated image. Okay, that's been done over here on the side. And it says verify that the dilation is a similarity transformation. All right. Now these can get a little lengthy because they're not always lined up perfectly with the coordinates that we know are 90-degree angles, but in this case for the triangles they are, so that's good. Looks like the original is A is -6, -3, 1, 2, 3, 4, 5, 6, -3. Okay, so we're talking about the big triangle here is my A shape, or my ABC, and the small one is this guy right here. And we are going to, okay, the original or the pre-image had these coordinates, the image has these coordinates, and what we need to do is we need to actually verify that each of the corresponding sides has the same ratio. So like I said, it's kind of like a hassle unless it's like nice triangles that are nice and lined up with the coordinate planes here. Just a reminder, we're comparing our scale factor is going to be image compared to pre-image, or original in this case is what it's labeled. Okay, so my image is this guy in the middle. So I'm going to go ahead and start with this side. I'm going to say 1, 2, 3, 4. I have a side of 4 over a side of 1, 2, 3, 4, 5, 6, 6. So I'm just comparing corresponding sides. And I also have another easily, I can find the distance easily just by counting 1, 2, 3, 4, 5, 6 over 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So I've got 2. I'm 2 for 2 so far. 4, 6, and 6 ninths. Their cross products will be the same of 36. Or I can think if they're reduced fractions, they'll be the same. But now the tricky one's going to be this guy right here. So I prefer the Pythagorean theorem. If I know this is 1, 2, 3, 4, and this guy is 1, 2, 3, 4, 5, 6, I can use the Pythagorean theorem to find my last missing side here, which isn't too bad compared to the quadrilaterals. Remember, on the Pythagorean theorem, it promises that each leg added up, if you square each one and you find the sum, will equal the hypotenuse squared. And so in this case, 16 plus 36 will equal c squared. 52 equals c squared. And then, of course, last but not least, the square root. As you're solving a quadratic function, you would need a plus minus sign. However, we are dealing with distance, so I'm going to disregard the plus minus sign on my quadratic function here, on my quadratic equation, I should say. 6 and 2. 13 and 2. So it does look like I can reduce the square root of 52 into 2 root 13. So there's my image. Ooh, no. That's 6. Yeah, my image is 2 root 13. And I'm going to, once again, I'm going to have to use the Pythagorean theorem to find this guy right here. Okay, so I know this guy's 1, 2, 3, 4, 5, 6, and this guy is 1, 2, 3, 4, 7, 8, 9. I know I already added those up together, but okay, let's go ahead and find the Pythagorean theorem to find that last distance that I need. I need all three ratios to be the same if they are really similar. So I'm going to say 6 squared in this case because it is a leg, plus 9 squared in this case because it is a leg, should equal the hypotenuse squared, just so we're clear on that. 36 plus 81 equals the hypotenuse squared. So it looks like I have 117, is that right? 117 is the hypotenuse squared. Oh, for goodness sakes, what's going on here? Let's go to 17. I bet, I bet 13 goes into 117. How many times does 13 go into 117? 9 times? 13 times 9? Whew, I was worried. Okay. So the hypotenuse in this case would be the square root of 117. I'm going to reduce that. And the reason I guessed 13 right off the bat is because I knew that I would have to have a 13 for this to reduce into the same fraction as everything else. So 13 times 9. In this case, there's a prime number, 3 and 3. I'm going to say 3 root 13. So if I reduce all these fractions, I get 2/3, 2/3, and 2/3. So I know for sure that they're similar, and I verified that. So I just want to walk you through, I just want you to look at this because I'm going to run out of time to do this whole next example. This is a quadrilateral, and it's the same idea, except for unfortunately on this one, and it would take me probably longer than 5 minutes to finish this one. I'm going to have to use the distance formula a lot because I don't have any that I can just count right away. You might have a little bit of luck if you don't like the distance formula making some right triangles, but I mean, I just think you just need to go through the distance formula and knock it out that way. You just need to make the comparison of each side length, just like what we just did. And so instead of me taking your time up doing more distance formula that I know you already know how to do, I'm going to refer you back to this one again and say, listen, you have to prove that these are similar, to show that they're similar, the ratios must be the same on all sides. So on this example, you should have 4 ratios, one for each side length that are all equal. Okay, it's got to be proportional on all fronts. And so once you've shown that, like I said, you're going to have to do some work to get the distances that you're looking for, then you're golden, and you have verified that they are similar. So that's it for today.